Now, there are two different types of acids that we need to be concerned about, okay? And it's important to understand that when we say strong acids or weak acids, we're not necessarily talking about how dangerous an acid is, okay? So I can have a weak acid that is extremely dangerous. For example, HF in our example here. HF is extremely corrosive. In TV and movie fame, in the show Breaking Bad, one of the early episodes, the main character uses HF to dissolve a human body. And it will readily do that, even though it's technically classified as a weak acid. So don't confuse the terms strong and weak for dangerous versus safe, okay? What it means is that strong acids completely ionize in water. That means that they completely come apart. Okay? All they do is come apart. So my HBr, for example, the only thing that it does is come apart. Okay? Now, with weak acids, what happens is that some of it comes apart and some of it comes back together. So they partially ionize in water. Okay? So my HF, the reaction will go to the right, and I'll get H3O plus and F minus. But you see this double arrow here? That means that the reverse reaction is also happening. So some of my F minus and my H3O plus is coming back together to make HF. Okay? But when we have a weak acid, so basically anything that's not in the left-hand list here, right? Anything that's not on that list is going to be classified as a weak acid. Okay? So weak acids, we're going to have mostly the unionized species here. So most of what's in solution, 98% of it, is HF. Okay? So if I were to, I'm going to come down here and draw a bit of a picture. So if I had a beaker of weak acid, I would have mostly HF in here with a little bit of F minus and a little bit of H3O plus. Okay? Most of what's in that beaker is going to be the original acid, just with a little bit of parts broken apart. Okay? So that's an important thing to remember. So strong acids completely come apart. Okay? So if I put some HBr in water, all I get is H plus and Br minus. But if I take some HF or some HNO2 or some other kind of weak acid, most of it is going to stay together in the solution. Okay, some of it comes apart, but most of it stays together. Okay, so when we have weak acids, okay, and this is kind of a little bit strange, the image didn't transfer very well to my recording, but it kind of did. So when we have weak acids, what you have are what's called conjugate pairs. Okay, so my acid, when it loses its proton, okay, we're going to find it just like we did before. We're going to find this HC2Cl3O2 on the other side. Okay, and so we see that it's lost a proton, so that makes it the acid. What it becomes, it becomes a conjugate base. Okay, so and the point of it is if I look at the reaction in reverse, if I look at it going from right to left, my C2Cl3O2 going right to left has picked up a proton, so then it acts as a base going right to left. Okay, but the easiest thing to realize is that your acid becomes a conjugate base. That's all you really need to know. Okay, acid becomes a conjugate base. So if you find what it becomes on the right-hand side of the equation, it's just the conjugate. Okay? And if we look in our equation here, my H2O has picked up a proton, so that makes it the base, and the base becomes the conjugate acid. Okay, so whatever it becomes is just the conjugate of the other word. Okay, so I want you to, don't worry about trying to think of things in reverse. Okay, I explained it that way so that you understand why we call it conjugate base when it starts out as an acid. But what I really want you to focus on is that acid becomes a conjugate base and the base becomes a conjugate acid. Okay, but you want to start by identifying the acid and the base, and then what they become is the conjugate of the other thing. Okay, so this is kind of a silly little image, but the idea here is that the acid dog, see the acid dog has an H plus on it, becomes a conjugate base, right? They're the same species, but just without the proton. So my conjugate base dog no longer has the proton. My cat does. So we could say the cat is the base, and then the H plus cat is the conjugate acid cat. Okay? They're the same species, just with the proton transfer. Okay? So let's do a little practice. All right, so identify who is the acid and the base. That's the starting point. Okay, let's find the H2O on the other side of the equation. So H2O becomes H3O. So it's picked up a proton, so that means that the H2O is a base, and what it becomes is the conjugate acid. Okay, then I'm going to change colors so it's a little easier to see. My HF, I'm going to find it on the other side. The HF has become F minus, so it's given up a proton. So that makes HF my acid, and what it becomes is the conjugate base. Okay, so the trick is identify these first, okay, and what they become are the conjugates. All right, let's look at our next example here. All right, so HCl, let's find HCl on the other side of the equation. HCl, find it right there. HCl has lost a proton, so that makes it the acid. And what it becomes is the conjugate base. Okay, and then my other one, let's find that HNO2. Find it on the other side has become H2NO2 plus. All right, but recognizing that that NO2 part is still there, all right, but it has one more proton than it did before, so that makes it the base. And what it becomes is the conjugate acid. Okay, but again, you want to identify the acid and find what it becomes, and then identify the base and find what it becomes. So, which image best describes an aqueous solution of HNO3? Now, HNO3 is a strong acid. Okay, so all it does is come apart. Okay, so if I have a strong acid in water, all I should have are H pluses and NO3 minuses. Or we could say H3O pluses because we're in water. Okay, so I should have none of this. No HNO3 should be there because it's strong. Okay, so and that's going to be this first one. Okay, if we look at beaker B, there's some HNO3 that's still together. That's not right. My beaker C has some OH minus in there. That's not right. And my beaker D has some separated oxygens and some separated nitrogens, and that's not correct. Okay. Remember, HNO3 is a polyatomic ion. Does not come apart. It stays together. Okay. Now, NH3 is a weak base, recognizing that part, weak base. So that means that some of it's going to stay together and some of it's going to come apart, but most of it's going to be there. NH3 plus H2O. It's weak, so it goes both ways. So I'm going to have some NH4 plus some OH minus. Okay, but most of it is going to be this. Okay, most of it's going to be the NH3. So let's find, so I should have some of this, and some of this in my beaker. Okay, so let's find the one that has all three of those things there. So our first one just has H3O pluses and OH minuses. Our second one has some NH3, some NH4, and some OH, but there's more NH3s than anything. So that's going to be our correct one. In our following reaction, water acts as and we can identify this. So find the HCN on the other side. So the HCN becomes Cn minus. So that's going to be my acid. It's lost a proton. It has one fewer hydrogens than it did before. And my H2O has become H3O plus. So it has one more hydrogen. It's picked up a hydrogen. It's accepted one. So that makes it a base. Okay. So the water, is it a Bronsted-Lowry acid? Has it lost a proton? Nope. A Bronsted-Lowry base accepts a proton. Yep. Is it a precipitate? Are there any solids in there? Nope. All right, my H2O is not a conjugate acid because the H3O is the conjugate acid, the thing that it becomes. And then my conjugate base is the Cn minus, the thing that the acid becomes. All right. Ammonia NH3 is a weak base, so what is the conjugate acid of ammonia? So if it's a weak base, it's going to pick up a proton, right? It's going to have one more proton than it did before. So what it becomes is NH4 plus, right? So here's the base, and what it becomes is the conjugate acid, right? So if you want to know the conjugate acid, all you got to do is add a proton or add a hydrogen to it. Okay, and we'll find NH4 plus is on our list. Okay, so anytime you have to figure out what is a conjugate acid of something, just put another proton on it, put another hydrogen on it, and you'll get the right formula. Okay, acetic acid is a weak acid. Which species has the highest concentration in an acetic acid solution? Okay, so if we remember, when we have a weak acid, most of it stays together. Okay, so if we look at the equation going left, we see it coming apart. But with weak acids, most of it stays together, right? So the thing that we should find the most of in there is the acetic acid. Acetic acid is vinegar, by the way, in case you didn't know. Vinegar is a weak acetic acid solution. Which solution has the highest concentration of H plus ions? Now this is exactly like we did in one of our previous chapters when you were asked to figure out what is the ion concentration. I think that was with the colligative properties chapter. Right? But this is exactly the same process. So if we think about it, our NaOH comes apart into Na plus and OH minus. Right? So I don't have any H pluses there. HCl becomes H plus Cl minus, so could be this one. NH3 doesn't come apart at all. Barium hydroxide becomes barium 2 plus 2 hydroxides, right? So no H plus is there. And this last one is acetic acid. So I get some H pluses and some C2H3O2 minuses, right? But let's think about it. Hydrochloric acid is one of our strong acids, and acetic acid is one of our weak acids, right? So even though I start with the same concentration of both, remember, weak acids pretty much stay together, right? So most of it's going to stay HC2H3O2, but all of my hydrochloric acid is going to come apart.